Calculus 1 video lecture number 2, the limit of a function. Now, something to keep in mind when we talk about the limit of a function, we're not necessarily referring to the value of the function, but rather what values or where the graph is tending towards as x approaches a certain value. So to differentiate these two and to kind of help develop this topic, we're going to look at a function that we should be super familiar with, f of x equals x squared plus 2. And we're going to look at all of the values on this function, on this parabola, near x equals 2. So let's start off by sketching the graph. So this is a parabola opening upwards, and it's been shifted up 2 units. So the vertex is going to be at 0, 2, and then we can go ahead and plot a few other points. If x is 2, I can just plug that in. F of x is going to be 6, so 1, 2, 3, 4, 5, 6 up here. I can reflect that point over there, and here's my graph. All right, and then let's indicate this is 1, 2, 3. And I'm interested in this case at the values of f of x, so I want to know the function values, the y values, the ones on the parabola, near x equals 2. So x equals 2 right here, so I want to look at what's going on near there. So for x values smaller than 2 and for x values larger than 2, what are the y values? What are the function values? Well, the best way to organize this information is just to make a table. Okay, so on the following page, we've got this little table here for x, f of x. And remember, in this case, f of x is equal to x squared plus 2. And I'm investigating near 2 because that's what the directions told me to do. Okay, so let's just start. If I want to know the function values at any of these other points, I'm just going to plug them into the function. So f of 0, that's going to be 2. F of 1 squared plus 2, that's 3. F of 1.5, that's going to be 4.25. F of 1.9 is going to be 5.61. Remember, we're investigating near 2, so we're just skipping it right now. I want to know what's going on either side of 2, on the left side and the right side. So if I plug in 2.1 into the function, I get 6.41. If I plug in 2.4, we get 7.76. If I plug in 2.9, I get 10.41. And if I plug in 4, I get 18. Now, of most interest are the values that we plugged in for x that are closer to 2, right? Since we're investigating near 2. So these are the closest ones. And can you see something about what the function values are tending towards? Well, it looks like that as the x values approach 2, then f of x, or the function values, approach 6. And we write this as follows. So we write that the limit as x approaches 2 of f of x is equal to 6. Now, in this particular case, 6 is also equal to the value of our function when x is equal to 2. But we're going to look at a few other cases now where that's not always going to be so. All right, so here we begin our definition. This is the notation that you need to learn and get comfortable with whenever you're dealing with a limit. All right, here's our definition. We say the limit as x approaches a of f of x is equal to L if we can make the values of f of x arbitrarily close to L, so as small or as close to L as we want, by taking x sufficiently close to a, but x is not equal to a. We're going to get into exactly how to deal with this definition in a future lesson, okay? But just make sure you understand how to properly write out a limit, okay? X approaches a, so that's the x value that we're approaching, and f of x equals L, that's always a y value. And we're going to look at 3 cases here where the limit as x approaches a of f of x is equal to L. This first case, case 1, this is similar to the parabola that we just looked at. When you're thinking of a limit, think of a little person walking on a graph. And in this case, this person's approaching a. They're approaching the x value a. And if they're walking on the graph, the limit is the y value that they're approaching. Well, in this case, the y value that they're approaching is L. And you have to check, we're going to get into this, from either side, right? Who's to say which way the person's walking towards A? And in case 1 here, the function value, f of A, is also equal to what the limit is. Okay, now look at case 2. Things are getting a little different here. So you're still walking on the graph. Here's where x is equal to A. So you're walking that way from either side. Maybe you're walking this way. And once you get very, very close to A, what y value are you near? Well, it looks like, again, the limit is going to be L. You're near the y value of L. Notice in this case, there's an open circle on the graph. So the value of the function is not equal to L when x is equal to A. The function value actually is defined to be m at that particular point. However, when you're talking about the limit, it doesn't depend on what the function value is. The limit depends on what the function is tending towards as you approach that x value. And then one more case here, where again we have a limit. So you're walking on the graph towards A, and when you get pretty close, it looks like you're going to be at a height or at a y value of L. Is the function equal to L at that point? Nope, I see another open circle here. What is the function equal to at A? Well, it's not defined to be anything there. That's fine. It doesn't mean we have any problems with the limit. Okay, so when you're looking at limits, remember, it's not necessarily what the function equals. It's what the graph is tending towards as you approach that x value. At this point, we're going to look at tending towards those x values from either side, from the left and from the right. So let's look at another example where we're going to observe or estimate a limit. We're going to use a table of values to estimate the following limit. It's the limit as x approaches 0 of tangent of 3x over tangent of 5x. So whenever you're going to use a table to estimate a limit, you want to plug in some values that are smaller and some that are larger than the value of A. In this case, this is A. And then this here is my f of x. So f of x is tangent of 3x over tangent of 5x. Okay, so we're going to approach 0. Let's do a few smaller than 0 and then a few larger than 0. We'll start with negative 0.7. You can kind of do whatever you want. Negative 0.1. I wouldn't plug in negative 10 though. That's not close to 0, right? So if you're estimating a limit, you don't want to get too far away from the value of A, because who's to say what's going on the graph if you get too far out of bounds. And then as you get closer to the value, squeeze in a few more, you know? So let's do negative 0.01. I'm going to skip over 0 for 2 reasons. One, I want to look at the limit as we approach 0, not necessarily what's going on at 0. Other issue, I can't plug in 0. Tangent of 0 is 0, so I would have 0 over 0 for this limit. Okay, let's go to the other side now. So 0.01, 0.1, and 0.7. All right, good. So all of these, just punch them in your calculator. Make sure you are in radian mode. Oh, yes. So you should start off with negative 4.56, 0.566, 0.5997, and then look at this. We get the same values back. 0.5997, 0.566, and negative 4.56. So as we get close to 0, any suspicions about what it appears the limit's going to be? It appears that the limit as x approaches 0, now you always have to write the function in, so you're going to have tangent of 3x over tangent of 5x. It looks like that limit is 0.6. Okay, that's just by observation. Now, when you're asked to actually find a limit on an exam, it is never okay to use a table of values. So only if the directions instruct you to do so is it fine. Otherwise, we're going to learn in this unit all of the different techniques for how to find limits conclusively using limit laws so that you're not just making tables and observing and making educated guesses. Okay, so using a table is not okay to find a limit conclusively or with any certainty. It's just observing or on an exam. If the directions say do it, then you do it. But that will just be a homework exercise if you're one of my students. Okay, now we're going to look at one-sided limits. We're going to look at a special piecewise function. We're going to call it h of t. And h of t is equal to 0 if t is less than 0. And then it's equal to 1 if t is greater than or equal to 0. So here's my t-axis. Here's h of t. So h of t is 0 if t is less than 0. So I'm going to have an open circle here to the left. And then h of t is equal to 1 if t is greater than 0. So say that's 1. Closed circle there. The graph goes this way. Okay, so now let's investigate this a little bit. First question says, what is the limit as t approaches? Now, do you see this little minus sign next to the 0? What that means is we are approaching 0 from the left. Ooh, okay. So what does that mean? That means when you're walking towards 0, you're coming from the left side, this way. So as you're walking on the graph, getting closer and closer to 0, but from the left side, what is the limit or what is the y value that you're approaching? Well, it looks like the limit as t approaches 0 from the left, remember you have to write your function in here, of h of t, don't leave that out, is equal to, if you're walking on this path, what's the function value approaching as you get close to 0? It's 0. Now, when you actually get to 0, that's not what the function value is, but remember, that's not what the limit is talking about. The limit is talking about where you're tending towards. If a GPS was tracking you, as you're walking towards 0 from the left, it would show that your height or that your y value was close to 0, or at 0 really the whole time. Okay, let's switch it up. So what is the limit as t approaches 0 from the right of h of t? So when you see this plus sign here, that means now you're coming from the right. Okay. So let's draw our little person in here walking on the graph. This time they're coming from the right side. This way. Okay. So as you're walking on the graph, approaching 0 from the right, what's your height? What's the function value? Make sure you write this all out properly. So the limit as t approaches 0 from the right of h of t is equal to, in this case, it's 1. Okay? So here we've looked at an example of a left-hand limit and a right-hand limit. And here's our following definition. We say the limit as x approaches a from the left of f of x is equal to L. That's our left-hand limit. And then similarly, our right-hand limit we write as the limit as x approaches a from the right of f of x equals L. Now, what if I were to ask you, what is the limit as t approaches 0 for h of t? So now I'm not specifying which side I'm coming from. So can you answer the question? If I don't say whether or not we are approaching from the left or from the right, can you tell me what the limit is? No, because these two values are different. So if I'm not specific in saying which side we're approaching 0 from, this doesn't have an answer. In this case, you would say it does not exist. All right, and here we have a very important fact to remember. So the limit as x approaches a, notice this is a two-sided limit because we're not saying what side we're coming from, which means it could be either. It could be either side. So the limit as x approaches a of f of x equals L, if and only if, so when you see that I double F, that you don't say if, it's if and only if, both the right-hand limit equals L and the left-hand limit equals L. So the right-hand limit and left-hand limit are the same. Okay, and this is the two-sided limit. So you're approaching from either side. So that should make sense because basically, if you're not specifying which side you're coming from, right? If you're saying, oh, what's the limit as x approaches a, then it shouldn't matter. It shouldn't matter if you're approaching from the left or from the right. If they're the same, then your limit will exist and you'll have an answer. Okay? All right, let's look at an example now where we can practice applying all of this. So here we have some graph. Don't worry what the equation would be. It would be something outrageous. We're just going to use the graph to answer the questions here. Okay? So part A. What is the limit as x approaches -3 from the left? Okay, so we're approaching x equals -3, but from the left side. So from this side. So you've got your little person walking on the graph this way. And as we're approaching -3 from the left, what does the function value look like it is? What's the y value? 2. Very good. Now, let's go from the other side. So what's the limit as x approaches -3 from the right? All right, if I come from the other side, this way, from the right side, it looks like we're going towards the same place in this case, right? So the limit is again 2. Good. Now look at part C. It's asking for the limit as x approaches -3, and this is a two-sided limit. It's not specifying from which side. So what you need to do is check what we already found in A and B. What were those two limits? Notice they were equal. So that means the limit as x approaches -3 of f of x is equal to 2. If these had been different, if A and B had not had the same value, then part C would not exist. We would write D and E for does not exist. All right, now part D is asking for f of -3, meaning it wants the function value. What is the actual value of the function when x is equal to -3? So look at the graph. And since we have an open circle, that means the function is not defined at -3. Do you see another circle filled in somewhere where x is -3? I don't. So f of -3 is not defined. Undefined, not defined. Okay, very good. Next one, we're going to look at the limit as x approaches 0 from the left of f of x. Okay. So we're approaching 0 from the left. So here's x equals 0, but we're going to approach it from the left on the graph. So find the graph, walk towards 0 from the left. What y value are you approaching? It looks like 1, yes? Good. Now part F, the limit as x approaches 0, this time from the right. Okay, so if I'm on the graph approaching x equals 0 from the right, what y value are we approaching? Pretend you're walking on the graph. The y value you're approaching is -1. Remember, you're walking here, getting close to 0. The limit is the y value, the function value you're approaching. So now in part G, it's asking us for the limit as x approaches 0. It's not specifying from which side. So this is a two-sided limit. So let me check. Are the limits from the left and from the right equal? No way. One was positive 1, one was negative 1. So in this case, this limit, don't put an equal sign, does not exist. It doesn't equal anything, so don't put that equal sign there. All right, do we have a function value at 0? Can I figure out what f of 0 is? I sure can. Look it over here. My actual function, we have a closed circle there at 1. So f of 0 equals 1. Even though we don't have a limit, we have one-sided limits. That's fine. All right, next one. The limit as x approaches 2 of f of x. Well, notice this is a two-sided limit. They didn't specify from which side. So we need to check both sides before we can answer this question. So let's look at the graph and see when x approaches 2, what the function's approaching. Okay, so here's where x is 2. Now go to the graph. If I approach from the left, it looks like the graph is approaching 2. If I approach from the right, again, I know it's really crazy out here, but when you're looking at a limit, you're looking at the function values close to the area of interest, which is when x is 2. So close to 2, in this little neighborhood, a little bit to the left, a little bit to the right, what are the function values? What are the y values approaching? Looks like they're approaching 2, right? So this limit exists, it's 2. And then finally, what is f of 2? What is the function equal to at 2? Well, maybe you already noticed, here we have a big old open circle. And it's not closed somewhere else for x equals 2. So it is undefined. Okay, no equal sign, no equal sign. Good, good. Now, we're going to move our discussion into infinite limits because we know not always do our graphs tend towards finite values. So here we're looking at the graph of hopefully a very familiar function, y equals 1 over x, and we know that this function has a vertical asymptote where x is equal to 0. You probably remember that from pre-calculus. So notice here, if I'm looking at the limit as x approaches 0 from the right of my function, okay, so here's x equals 0, right? And imagine you're walking on the graph and you're coming towards 0 from the right side. So you're walking on the graph from the right. My goodness, it's getting steep, right? And as you get closer and closer to 0, what y value is the function approaching? Where are you going? All the way up to positive infinity. My goodness. Now, what if you approach 0 from the left? So this time you're walking on the graph. Maybe you're walking upside down, huh? You're walking on the graph, getting closer and closer to 0 from the left side. Where are you going? Where are you tending towards? In this case, negative infinity. And we know that x equals 0 is a vertical asymptote. And the way that we show it, now that you're in calculus, is by finding the limit as x approaches some value. Anytime it comes out to be positive or negative infinity, that means you have a vertical asymptote. So, in general, we say that x equals a is a vertical asymptote if at least one of the following is true. So you can either have a two-sided limit or any of the one-sided limits from the left or from the right. If any of them is positive infinity or negative infinity, that means your graph starts blowing up in the positive or negative direction as you get close to that x value. And graphically what that means is you have a vertical asymptote. So you have ways of finding it in pre-calculus, right? Based on if you have a rational function and finding where the denominator is 0 after it's been reduced, so on and so forth. But now in calculus, we have another way to find where vertical asymptotes are based off of limits. All right? So let's look at a couple examples here, and then we will be done. So examples, determine the infinite limit. So let's see what's going on. They're telling me we're approaching 5 from the left-hand side, and we're looking at x plus 1 over x minus 5. All right, so what I notice is as x approaches 5 from the left, this denominator is approaching 0. And then as I approach 5 from the left, the numerator is not approaching 0. It's approaching some constant. What I want to know is whether the sign of the entire expression is positive or negative. Why do I want to know that? Well, let's think about it. The numerator, as x gets close to 5, is getting close to 6, and the denominator is getting close to 0. So if you have a non-zero constant over something that's approaching 0, think about what's happening to the entire quantity. If the denominator is getting smaller and smaller and smaller, then that means this expression is getting bigger and bigger and bigger. So this is either going to approach positive infinity or negative infinity. So what I want to know is it approaching through positive values or negative values as it gets bigger and bigger and bigger? So a couple ways you can test. You could make a table, or what I like to do is make a number line. So you want to list all of the zeros of the expression on the number line. So I've got -1 and 5. And remember, I'm approaching 5 from the left, okay? I'm approaching 5 from the left. So I'm just interested in testing what the sign of the function is here. That's it, actually. I don't need from the other side because it's only a one-sided limit. Okay, so pick a value close to 5 from the left, maybe 4.9. If I plug in 4.9 into x plus 1, that's positive. If I plug in 4.9 into x minus 5, that's negative, which means the sign of the entire function near 5 from the left-hand side is negative. And then we already discussed, as the denominator is shrinking, since the numerator is approaching a non-zero constant, the whole expression is blowing up. It's getting very, very large in magnitude. And since I know the sign of the expression is negative, then that means the limit is negative infinity. Okay, I'll say that one more time. So since the numerator is approaching a non-zero constant, right, just 6, think it's not changing really. And the denominator is approaching 0. So the denominator is shrinking, shrinking, shrinking. Then that means the entire expression is getting bigger and bigger and bigger. It's blowing up. And since we just checked that on the left side of 5, this expression, x plus 1 over x minus 5, this function is negative. It has a negative sign. Then that means the limit is negative infinity. It's getting really, really big, but in the negative direction. So putting everything together, how do you write your answer out? You write the limit as x approaches 5 from the left of x plus 1 over x minus 5 equals negative infinity. Make sure you rewrite what the original function was. You have the limit as x approaches 5 from the left. You write lim, and then you have the limit on the other side. Okay. Let's look at one more example. We have the limit, again, as x approaches 5 from the left, of e to the x over x minus 5 cubed. Okay, so here we go. Let's make our number line. Here's 5, and I'm interested in checking values from the left. So I want to know what's going on over here. Okay. Well, I'm working with e to the x over x minus 5 cubed. So pick a number there, maybe 4.9 again. So e to the 4.9, well, e raised to any power is positive, okay? And then 4.9 minus 5, that's going to be negative 0.1. If I cube it, it's still negative. So that means my function has all negative values in this interval. So the denominator is approaching 0. E to the 5th, that's a non-zero constant, which means this is approaching positive or negative infinity. Since I just checked that the sign of the function or the expression is negative, then that means the limit as x approaches 5 from the left of e to the x over x minus 5 cubed is negative infinity. Come back. Okay, let me ask you something though. What if instead we wanted the limit as x approaches 5 from the right of e to the x over x minus 5 cubed? Well, now this time I want to approach x from values that are larger than 5. So let's see what would be happening there. So e to the x, think of a number there, maybe 5.1. E to the x would be positive. What about x minus 5 cubed? 5.1 minus 5 cube it, it's positive still. So this time my function, or the sign of the expression, is positive, which means the limit as x approaches 5 from the left of e to the x over x minus 5 cubed is positive infinity. Okay. One more thing I could ask. Do you know what I'm going to ask you? What is the limit as x approaches 5 of e to the x over x minus 5 cubed? If I don't specify which side we're approaching from, then that means it's a two-sided limit. So you check. Limit from the left was negative infinity. Limit from the right was positive infinity. So what can we say about the limit as x approaches 5 of e to the x over x minus 5 cubed? That's right, it does not exist, since the limit from the left does not equal the limit from the right, because left-hand side and right-hand side limits are not equal. Okay. So that concludes the lesson. Stay tuned because we're going to look at how to calculate limits using limit laws in the following lesson and not relying on a table of values.